Okay, so these are gas laws. There are two types of gases. There are real gases, and the real gases, the molecules are large enough that the intermolecular forces affect how the particles interact with each other. Now, I know that sounds kind of silly, but you need to remember that gases only have dispersion forces, and dispersion forces get stronger as the particles get larger. So since gases only have dispersion forces, very small gas particles would have no intermolecular forces at all that affect them because they're super small, and that's the only particle they have. Okay? So these gases, these real gases, using quotation marks, real gases, these particles are large enough that their dispersion forces actually do affect how they affect each other because they're large enough, all right? And they have a huge amount of energy. So it's not like a solid, which doesn't have a lot of energy, because those particles actually, their dispersion forces do affect them, and liquids also. But gases have so much energy. And then now these particles are large enough that their dispersion forces affect them. Meanwhile, we also have ideal gases. Ideal gases have 5 different things about them that make them what we call ideal. And I have squished them down basically into 3. All right? So I've like combined them. So first of all, they are very small particles compared to their containers, compared to their volume, the volume around them, right? Oh, sorry, compared to the volume of space that they're in. Second, they are constantly moving. I'm trying to remember what the slide is, so they are constantly moving, constantly in motion. I can, but then my video is going to stop. It's right. It's all right. It's only this one. And then I have the thing. They're constantly in motion, and they're collisions, which means that they have more collisions, and their collisions are 100% elastic, which means elastic. And that means that they don't lose any energy to friction. It is a 100% energy transfer. And number 3, their intermolecular forces are negligible or non existent. So basically, what you have are these particles which are constantly moving and have virtually no forces attracting them to anything around them, which means that they are completely independent. And that means that they have no other forces, no forces at all, causing an imbalance or changing their behavior. So that makes their behavior completely predictable, which I know sounds like, no, wouldn't it be the opposite? But it's not the opposite, because the only forces that change their behavior are forces that we can predict. Things like the pressure that we apply, or the volume that we can predict how the volume is going to change. And so we have formulas that can predict their changes, because their changes are only due to changes that we apply. We don't have to account for forces that they are applying, because they have no forces being applied, because they're just reacting to our forces. They don't have any forces of their own. They're completely subjected to only our forces. So that's what we're going to be looking at today, are these formulas, okay? Now, the kinetic theory of matter, when it comes to gases, now I'm back into my PowerPoint, so that's good. Here we go. Which I can't put my PowerPoint up on the video, so I have to use slides. Okay, so the assumptions of the kinetic theory in matter are based on 4 factors. This is yeah, you have to write this, but this is the only other one that's got a lot of writing. Is based on 4 factors. And the 4 factors are this: the number of moles in the sample, which is a lowercase n. The temperature, which is an uppercase T and must always be in Kelvin. Always. For this unit, you cannot use degrees Celsius. You have to always switch to Kelvin. The pressure, which is represented by a capital P, and the volume, which is capital V. When you change one factor in an equation, that's going to affect the other factors. So if you increase the pressure, you increase the temperature. If you decrease the volume, you decrease the you decrease the pressure. Sorry, if you decrease the volume, you increase the pressure. I was like, that's not right. If you decrease the volume, you increase the pressure. If you decrease the volume, you decrease the temperature. You increase the temperature. Decrease the volume, increase the temperature. All right? So all of this is in the equations that we're about to look at. We're going to look at 3 equations today. There's something like 9 equations that we're going to have overall. They're all on the same thing. All use the same 4 variables, and then there's one constant, but they all use basically the same variables. The first one we're going to look at is Boyles' law. Boyles' law only has to do with pressure and volume. So we set up these conditions, the ones, so one, we have a situation where there's a set of pressure and a set of volume, and then we change the pressure. Using Boyles' law, we can determine what the new volume is. Now you can see that the pressure and volume are inversely proportional. And so what I want to do is, after you're done writing, we're going to take a moment and we're going to talk about what inversely proportional means. Okay, so let's take a look at inversely proportional. So let's say that I have a situation where I have a pressure of 4 and I have a volume of 8. These two combined for pressure 1 and volume 1 right? Make 32. So now I have pressure 2, which is 1, and volume 2, and they have to equal 32. And I know this because I can see over here that P1 times V1 is equal to P2 times V2. That's what the formula says. So P1 times V1 here is equal to 32. So I know that P1 times V2, P2 times V2 must equal 32. So you can already tell that V2 is going to equal 32. But let's look at it as an analytical perspective. So what I did here was multiplied the pressure times 1 over 4. Right? So 4 times 1/4 is 1. Now this is an inversely proportional relationship, which means that what I'm going to do is I'm going to multiply the 8 times the inverse of 1 over 4. So the 8 gets multiplied times 4. 8 times 4 is 32. This is an inversely proportional relationship. As one of them decreases, the other one increases by the inverse of that. Yes?
What if you have like different numbers? Like 5 and 6, would it be 1 over 5?
Great, so let's look at 5 and 6. So here is my pressure 1, which is 5, and my volume 1, which is 6. So let's multiply. Let's say my pressure increases to 25. Okay, so I'm going to increase my pressure to 25, which means that I multiplied it by 5, which means I'm going to divide my volume. I'm going to multiply my volume by 1 over 5. So my volume, so this is 30, right? So in order to get this to be 30, right, I'm going to multiply this by 1 over 5, so I get 6 fifths, right? Does that work? Well, 25 times 6 is 150, divided by 5 is 30. So it does work. Everybody understand? I'm going to multiply my pressure times 5 to get 25, which means that my volume will be multiplied by 1 over 5 to get 6 fifths. These two, 5 times 6 is 30. 25 times 6 fifths is equal to 30. Okay? This is inversely proportional. As one goes up, the other goes down by the inverse amount. Sorry. As one goes up, the other goes down by the inverse amount. Now let's take a look at the next formula, because the next formula is what we call directly proportional. This is Charles' law. Charles' law is directly proportional. It's volume and temperature. Remember, temperature must be Kelvin. Charles' law is directly proportional. Directly proportional means that as one goes up, the other goes down. So if I were to have 1 and 2 here, and I were to multiply my volume times 3, I would get 3 for my volume. I would then need to multiply my temperature times 3, and I would get 6 for my temperature. That would be the same fraction. It is still 1/2. Because this is directly proportional. What I do to one, I'm going to do to the other. In indirectly proportional, what I do to one, I do the inverse to the other. Okay? Now, I don't like fractions. I like linear equations. And so what I'm going to do is I'm going to cross multiply this. And that is going to give me V1 T2 is equal to V2 T1. For me, this equation is better. I like this equation better. All I have to do is remember that every time T comes into the equation, the T is on the wrong side. This is going to be useful for me for other equations. If you like the fraction better, please feel free to use it. You'll see that on your worksheets, this linear equation shows up again. So you can use linear or fractional. Both are on your worksheets, and both will always be in your notes. It's your choice as to which one you want to use, okay? Kelvin. All right, questions? Okay, third equation, the combined gas law. 2. So we're going to take both of those relationships. We're going to take Boyles and Charles' law, and we're going to put them together because sometimes pressure, volume, and temperature all change at once. So we need a way for those three to change. So we're going to take the pressure, the volume, and the temperature. And I'm going to give you the linear equation here, P1, V1. And then here comes P2. Because the temperature is always on the wrong side of the equation, of the equal sign. P2, V2, and there's T1. You can use either one. Both of them will work. Remember, temperature always has to be in Kelvin. All right, let's do some practice problems. So you're going to take out your worksheet, and we're going to do problem 1 on all 3 of the pages that you have for homework. Okay, we're going to start with problem 1 on Boyle's law. So a big part of this is lining up your ones and your twos, like your P1 V1s and then your P2 V2s. So we're going to start, first of all, at the top of the page is, okay, there we go. At the top of the page is the formula. On the top of all 3 pages is the formulas, okay? So next, I'm going to look, and it says a sample of oxygen gas occupies a volume of 250 milliliters at 750 torr. So my V1 is equal to 250 milliliters, and my T1, my P1 is equal to 740 torr. Next, my V2 is what volume will it occupy? So we don't know. That's what we want to find out. And my P2 is equal to 800 torr. So what I've done is I've very carefully in my reading grouped together the volume 1 and pressure 1 that go together. A gas occupies a volume of 250 milliliters at 250 torr. What volume will it occupy at 800 torr? And now I'm ready to write it out. So I get P1 V1 is equal to P2 V2. So P1 740 torr, V1 250 milliliters equals P2 800 torr V2. Now, what I'm going to do is divide both sides by 800 torr. Algebra. What I get to do is cancel out my 800 torr on this side, and I get to cancel my torrs on this side. Once I do that, I'm going to do my calculated work. So my calculator work, let's go back a little bit. There we go. Up a little bit. There we go. My calculator work is 740 times 250 divided by 800. And that's going to give me 2.31 times 10 to the 2. Milliliters is equal to V2. Are there any questions about the work I did? No? Okay. Let's go to Charles' law. Okay, in Charles' law, remember, all temperatures must be in Kelvin. And so there, right there, is the conversion. You're going to add 273. And here are both equations. Here it is as a fraction, and then here it is as a linear equation, which I prefer. But if you prefer the fraction, plug them in as a fraction. The benefits is that all your ones are on one side and your twos are on the other side. That's the benefit for the fraction. The benefit for the linear is that you don't have to face the fractions. So whichever you want to do. But remember, if you go linear, you have the temperature is on the opposite side that it should be, right? It's going to be with the ones. Okay, a sample of nitrogen occupies a volume 1, of 250 milliliters at 25 degrees Celsius. So there's my temperature. What volume, V2, I don't know, will it occupy at 95 degrees Celsius? T2, 95 degrees Celsius. So the first thing I need to do is to convert those temperatures into Kelvin. So I'm going to do that first. 25 plus 273. That gives me 298 Kelvin. And then 95 plus 273 gives me 368 Kelvin. Okay? And now I'm ready. So I write out my equation. V1 T2 equals V2 T1. And if you want to use the fraction, just write it out. And then I'm going to plug it in. So now I'm plugging in 250 milliliters. That's my V1. T2, 368 Kelvin. And then my V2 is what I'm looking for. I don't know. Times my T1, which is 298 Kelvin. I'm going to divide both sides by 298 Kelvin. By doing that, I get my V2 alone, and I cancel out my Kelvin. So now I'm just going to do my math here. And I only get 2 digits because of the 25 and the 95. So I'm going to round off 3.08 to 3.1 times 10 to the 2 milliliters. And that's my volume. Anybody have any questions so far at all? Okay, let's move on to combined. Page 3. It's all very similar. We're just doing the same thing. We have a different formula. There's your formula up there, both fractional and linear. So I'm going to use the linear formula. If you want to use the fractional, it's the same thing, all right? So the first thing I'm going to do here, remember you do not have to show your work, but I'm going to advise you again that you absolutely want to make sure that you're laying everything out. It's going to get more complicated, okay? So the first thing I want to do is convert my temperatures to Kelvin. 273 plus 20 is 293 Kelvin. 273 plus 30 is 303 Kelvin. Next, check to make sure all your units are the same for the formula. I have ATMs, that's the same, and Kelvin, that's the same, and liters, so I'm going to end up with liters for my answer. So now I'm going to lay out my formula. P1, V1, T2 equals P2, V2, T1. And now I'm going to plug everything in. So 1.5 ATM, volume 1, 3.0 liters, T2, 303 Kelvin, equals P2, 2.5 ATM, V2 is what I'm looking for. T1, 293 Kelvin. Now I'm going to divide out what I don't need, 2.5 ATM. And of course you don't have to do all this. I'm doing it so that you can see what I'm doing. 293 Kelvin. And then on the other side, I'm going to divide out 2.5 ATM. And over here, I'm going to divide out 293 Kelvin. Now, over here, I can cancel these two. When I do that, I'm left with V2, which is what I'm trying to solve for. So over here, I can cancel my kelvins, and I can cancel my ATMs. So that leaves me with liters, which is great, because I'm trying to solve for volume 2. Are there any questions so far? Okay, now I'm just going to go 1.5 times 3.0 times 303 equals, divided by 2.5, divided by 293, and my answer is 1.9 liters. And that is my answer. Any questions? Okay, you have about 7 or 8 minutes. This is a lot of problems. I would go back to the first page and do as much as you can. You might even be able to finish the first page. Okay? I would not waste this time. All right?